think there's no one else. Just one moment. Let's start in bit.
Excuse me, sir.
Yeah.
So can I ask a doubt?
Is it from week 4, the last session?
Sir, no, it is from the graded assignment of week 3.
Yeah, sure. Let's quickly, if I can't do it within say 5 minutes, let's take it up at the end. All right. Yeah, go ahead.
Sir, the week 3 graded assignment, question number 8, 9, and 10.
You'll have to give me the question. I don't have the thing ready over here.
So can I share the screen?
No, just tell me the question. Let's quickly go. Okay, maybe let's take it up at the end. Is that fine?
Okay, sir.
Okay. If there are 3 questions, no, probably it will take some more time. So let's take it up at the end. I've put the link to the stream in the chat. Let's get started. So last time we had seen bases. Towards the end, we defined them, but the idea behind basis in a vector space is that we are trying to find some representative elements, certain finite number of elements, such that every element can be written as a linear combination of these elements. Right? So that was what a basis is. And it's not so if any element can be written as a linear combination of elements from a given set, that set would be called a spanning set. Basis is something which is slightly more special. It also needs to be linearly independent. This allows us to have unique representation. So every element can be uniquely written as a linear combination of given elements in the set. So that was what a basis is. Equivalently, we formulated it this way: a linearly independent spanning set. So two conditions that need to be checked are: is it spanning? Is it linearly independent? And equivalent formulations was a maximal linearly independent set. Li would stand for linearly independent, and a minimal spanning set. So what is maximal linearly independent set? It is a set S such that, assume there is a vector space V in the background and we are working in that. So such that S is linearly independent and any superset of S is linearly dependent. I'll just call it LD again. So it should be linearly independent, and you cannot have a bigger linearly independent set. So if you add any element, the linear independence property will go away. Such a set is called a maximal linearly independent set. There cannot be a bigger one. By bigger, I mean there cannot be a set which contains this set, which is also linearly independent. Similarly, a minimal spanning set would be a set which is itself spanning, and any subset of it cannot be spanned. So with this, all these 3 conditions, 1, 2, and 3, are equivalent. So you can use either of the conditions to decide whether a set is a basis or not. Now, number of elements Suppose I'm given a basis. Okay, let's say base B is some basis for B. And let's say I have another set S1. This is a spanning set. So number of elements of B and number of elements of S. What is the relationship between the number of elements of B and number of elements of S?
Less than equal to. Is it less than equal to?
Is it less than or equal to or greater than or equal to? It has to be one of the two. What do you think it is? If it is less than or equal to, can you justify why?
Because basis is a minimal spanning set, right?
Yes. So it is actually less than or equal to. Oh, so this is S1. And if you have any linearly independent set, then what would be the relation?
Greater than equal to.
Yeah. So this is something that follows directly from this. There is one subtle point which we have not addressed actually, that a vector space. Okay, now the recap is done. Let's take a new page. A vector space can have many bases. Bases being the plural of bases. So let's take for an example R2 itself. What is the standard basis for R2?
1001.
Yeah, these are the standard basis vectors. We had seen that this actually forms a basis. Now let me take something else. Let's say 1121. Is this a basis?
No.
Which condition is not satisfied from?
It's
So there are.
it's not linearly independent.
Why is this not linearly independent?
1 1 is into 2 becomes 2 1, right? Like we can represent one as a multiple of other.
1 1 into 2 is not 2 1.
Oh,
It
okay.
is.
Okay, sorry. Yeah, my bad.
It's 2 2, right?
Yeah, yes.
Yeah. So that it is linearly independent is fine, because these two are not multiples of each other. This is a linearly independent set. To see whether it is spanning, you'll have to do a little bit more work, but you can do that. You can see that this is spanning. This is also a basis. With more generally, if I have a set B, which is V1, V2, both are non-zero elements, V1, V2 non-zero, and not multiples of each other, not multiple of one. Well, in that case, I can maybe even remove this condition. If this is a linearly independent set, would imply this is a basis. This is a slightly more involved statement. We're not going to prove it, but this is a fact. So how many bases does R2 have?
Infinite.
Yeah, so you can have infinitely many choices of this thing. Take for even just taking B1, I can change B1 a little bit more. I can write B1 prime as 1002, or just another change. I'm not going to, I cannot possibly write everything. If I even just write 1.5, this is also fine. 1, 0, 0, whatever will work as a basis. So that itself will tell you that there are infinitely many bases. So when I talk about comparing the size of the basis and the spanning set, if different bases could have different number of elements, then that would be a problem, right? Like say there is a, for R2, if there is a basis of which contains 3 elements, but then the spanning set, you cannot compare any spanning set with any basis. That becomes a problem. But that actually is not a problem because of the following fact, which will not be proved. Any basis of a vector space has the same number of elements. See, this number is slightly wrong because there are infinite dimensional vector spaces, but in this course, you'll be only dealing with finite dimensional vector spaces, meaning every vector space that you will be given, you will be working with, will have a basis which is finite. Okay, infinite dimensional vector spaces is not part of this course. So that's why I'm just using number. Otherwise, number of elements of an infinite set is not a precise state. But in this case, for the vector spaces that we'll be dealing with, there will always be a basis of finite elements, and any other basis, the basis itself, they may be different, but the number of elements that they have will be the same. Just as we saw over here, you have infinitely many bases, but each basis has only 2 elements. Is it possible to span R2 with just one element? At least we can see that that is not possible, right?
No.
Yeah. Do you see why it is not possible to span R2 with one element? Can you quickly give the argument?
We need to have n number of elements for spanning RNs.
Yeah, that's a fact
spanning
that
n
we
number.
want to establish now. But if I take one element and look at its span, what does it become?
It will represent only one axis, sir.
Not necessarily one axis.
Effectively,
It could be something like
a
it will be a
line.
line through. Yeah, it's a line through the origin. So it's not necessarily an axis, but it's just a line. A line cannot cover the entire plane. So one element does not do. A 3-element set cannot be a basis. Is, well, you can later on when we see how to check the span of certain things, you will see that 3-element sets also cannot do this. Every basis has to be of 2 elements. In general, different bases for a given vector space, different bases will have the same number of elements. And this number is what is called the dimension of the vector space. Number of elements in a basis, doesn't matter which one because of the above fact. Number of elements in a basis for a vector space is called its dimension. There is this other nomenclature of rank, but I avoid it because rank is also used in the context of matrices, and those things are related, but let's stick to dimension for now. Let's take up examples. The only way to understand theory is by examples, right? Rn, the most trivial example. What is dimension of Rn?
Sir, n.
N.
Yeah, and why is that?
We cover definition is the number of elements in a basis for a vector space.
Okay, so give me a basis with n elements.
we can just take it trivially, like 100 like.
So if you take the standard basis, is what it's called. It's not the trivial elements. So the standard base is E1, E2, En. This in the last session we have seen, or even you can just check it now, that this is a spanning set, which is also a linearly independent set. So this is a basis. It has n elements. So the dimension of this is n. In general, if you're given a vector space and you're asked for its dimension, what would you do? You try to construct a basis and count the elements, number of elements in that basis. So let's try to do that for a couple more things. Let's say V is M2 cross 3 R, which is, I'll not write the mathematical description, vector space of 2 cross 3 matrices. What is the dimension of this?
6.
Sir, 6.
So let's try to write a basis for it first. Then we can.
Sir, 2, sir.
2, sir.
Okay, there are candidates 2, then 6.
It's 2.
Okay,
6.
can you give me a 2-element set which is a basis for the space of 2 cross 3 matrices?
1 0 0 0 1 0.
0 0 0 1 0. 0 1 1.
1 0 0 0 1 0. So this is your first
Sir,
element.
0 is 1 1.
Yeah.
Okay, you can take this. That's your first element. And what's the second element? So your vectors are matrices, remember. Now you have to give me 2 matrices which span the whole thing.
Zero 1 0 1 0 0.
So if you do 0 1 0 1 0 0, do you not see that this will be insufficient?
No, sir. It will be 0 1 1 and 1 0 0.
Okay. So is this the final candidate?
Yes, sir.
Okay. Now, what about the matrix 0 1 0 0 0 0? This is a matrix in our vector space. Can it be written as a linear combination of these two things? Can I write C1 times
No,
the
sir.
first matrix plus C2 times the second matrix is equal to this? Is it possible?
No, sir.
No.
Now, what happens if I simplify this? Let's take it step by step. C1, C2, C2. This is just me doing taking the C1 and C2, multiplying it inside and then adding pointwise. This would give me 0 1 0 0 0 0. So we would get C2 is equal to 1 as well as C2 is equal to 0. Well, this also gives me C2 is equal to 0. So I run into a problem, right? It's not possible to express this as a linear combination of the given two vectors. So one of two statements is correct now that, okay, this is not a basis or this is not even a spanning set. That much is clear. So either the dimension is not 2 or you have chosen wrong matrices as the basis. Which is the correct statement?
Use the wrong matrices.
Okay, so you can give a 2-element set which spans a given vector space. So can you give me the set of elements?
First of all, I know actually you can 1 0 0 and then comma
Now you have to give me two matrices, right? First one is, what is the first one?
Okay, first one is like 1 0 0. Downside all the 0 0 0. On
Okay.
top of it, second one on top all 0 0 0.
Okay.
And 0 1 0.
But this will not span, no? Any linear combination of this will have the third column as 0 0 itself. Take, for example, 0 0 1 0 0 1. This will never be in the span of this set.
But if we add the both, and it
Yeah.
has only two pivot elements.
Yeah, if you add it, it has two pivot elements is not the way to see it, right? So when you claim that this is a basis, it means that you're saying that every element can be expressed as a linear combination of these two elements. But that is not happening over here. Right? Do you understand the point that I'm making?
So what is the correction
Yes,
here?
sir.
So both our attempts have failed because, okay, so let me just write 0 0 1 0 0 0, for example, does not belong to span of P2. So there was another guess, yeah, there was this 6. So whoever came up with 6, can you give me a set of 6 elements which span the whole thing?
For each of the
Let me just call
matrices,
it.
for each
Yeah.
of the matrices, we can have any of the entry as 1. So like 1 0 0 0 0, like something like
Yes. So okay.
That is correct. Yeah.
So for just this one time, I'll write it explicitly. It is having exactly one element as a 1. It is something like a standard basis for Rn. Instead of EI, we can call it EIJ, where only ijth entry is 1 and everything else is 0. Now, is this linearly independent?
Yes, sir. Yes.
How do we see that it's linearly independent?
We cannot express one matrix as the sum or like linear combination of another one.
What is the definition of a basis or of linearly independent? The first definition, the fundamental definition.
So let's take the matrix to be x1, something like that. Then a1 x1 plus a2 x2 till a and xn equal to 0. Then a1
Yeah.
a2 everything
So
has to be
I'll call this A11. I'll call this A12. I'll call this A13. I'll call this A21, A22, A23. Aij is the matrix in which ijth entry. Sorry, A22, A23. Aij is the matrix where ijth entry is 1. So if I take a linear combination which equals 0, which means I take something like Cij, Aij is equal to 0, then if you simplify this, I won't do all of the simplification. You'll just get C11, C12, C13. Here, remember that 0 is the 0 matrix. C21, C22, C23. This is equal to the 0 matrix. This forces all coefficients to be 0. So Cij is equal to 0 for all ij. A few steps have been skipped over here. Go back and do this. This is not very involved. You just set up a linear equation. You set up a linear combination of the given elements which equates to 0 and conclude that the coefficients are forced to be 0. This is the definition of linear independence. So this is B3 is linearly independent. That is fine. So the basis is any basis is of at least size 6. So you have a linearly independent set of size 6. Basis should be at least 6 elements. But then do you see that any element can be written as a linear combination of these 6 elements?
Yes, sir.
Yes, right? Because this is just like the standard basis. You can just remove that particular element and then write. So if I take any arbitrary element A, B, C, D, E, F, I can write it as A11 plus B, A12 plus C, A13 plus D, A21 plus E, A22 plus F, A23. So any element can be written as a linear combination of these given elements. So B3 is spanning. So B3 is linearly independent, B3 is spanning. What does that mean?
B3 is a basis.
B3 is a basis. And what can we conclude from that?
Dimension of B is 6.
6. This was what? Example 2, example B. So as a generalization of example B, like B prime or something, if I have the vector space of M cross N matrices, then what is the dimension of that?
M cross N.
Yeah, it's Mn. M times N. Once again, you will have the standard basis vectors, vectors being matrices over here, where only one entry is 1 and everything else is 0. You can call it like EIJ if you want. I've called it AIJ above in the specific 2 cross 3 context. But similar matrices, you can take it as an exercise. You can work this out. It's not much different from what we have done over here. So let's take a few more matrix subspace examples. So V is, I'll take specific examples. For any arbitrary size M you can do. A in M2 cross 2R such that, let's say, A transpose A is equal to A. What are such matrices called?
Symmetric.
Yeah, so the space of symmetric matrices is also a vector space. Because if you add two symmetric matrices, you will get a symmetric matrix. The scalar multiple of any symmetric matrix is again a symmetric matrix. So this is a vector space. That is the first point. And then what is the dimension of this? First of all, what is the dimension of M2 cross 2R? This is just from thing above.
4.
This has to be 4. It was Mn that we have already seen. So what do you expect the dimension to be, at least in comparison to 4?
It should be 4 or less than 4.
Less than 4, less than or equal to. It could, if it is the whole space, then it will be equal to, but otherwise it will be less than 4. So the dimension of a subspace is always less than or equal to the dimension of the whole space. So this is a subspace of M2 cross 2, right? So this will have lesser dimension, but how much? Let us see. So do you have a candidate for a basis for this?
1 and 0 0 1 and then 0 double 1 1
So
0
just one moment. Just tell me the first matrix.
1 0 0 0.
Okay.
Then the second will be 0 1 1 0, and the third will be 0 0 0 1. Yeah.
This is it.
Yeah.
So
I guess
you are claiming that dimension of V is 3, right? So is this linearly independent? Is this spanning? So which one shall we take up first, linear independence or spanning? Let's take linear independence first. So to check whether or not this is linearly independent, what do we need to do? Set up a linear combination which equates to
Sir, it's not linearly independent. This turns out to be linearly dependent, right? Because V2 can be written as a sum of V1 plus V3, right?
No, that is not the case. V2 is sum of V1 and V3 is identity. This V2 is one on the
Okay,
non-diagonal
okay, okay,
elements.
okay, okay, okay. Yeah. So you have 0, right?
So if I set up the linear combination which equates to 0, is 0 the only solution? Is the trivial solution the only solution? Is what we have to check for linearly independence, linear independence. So the question is, does this imply Ci is equal to 0 for all I? I've just put it in the bracket, but that is what we have in our mind. This is what we are going for. So when I simplify this, what is the matrix that I'll get? What is the equation that I'll get?
C1, C2, C2,
C1,
C.
C2, C2, C3.
This is equal to 0, 0, 0, 0. So this would imply that C1 is equal to C2 is equal to C3 is equal to 0, right? So the only solution for the coefficients which equate to 0 is just the trivial solution. So this is actually true. This is a linear combination of the given vectors equates to 0 implies that the coefficients are 0. This is precisely linear independence. Therefore, B, or what did I call it? B1. B1.
Sir, why we are not taking like in the earlier example 1 0 0 0 0 1 0 0 and like 4 matrices as the elements?
Let me get back to that after we finish this. That's a valid point. I'll come to that. Let us just finish this spanning set and then I'll come to that. Spanning. So if I want to say that B1 is a spanning set for V, then what is it that I have to show?
Any element in the set can be represented using the basis B1.
Yes. So what is any element in the set? What is a typical element in the set? What is an arbitrary element of the space of symmetric matrices? How can I write it?
The non diagonal principal elements are equal.
Yeah. So let's just give symbols. No? Just call them something A, B, C, and write down a typical element.
A0.
The general element would be A, B, B, C, right?
B0, BC.
A, B, B, C. So can this be written as a linear combination of these three elements? I'll just keep that.
Yes, it is.
So it is A times 1 0 0 0 plus B times 0 1 1 0 plus C times 0 0 0 1. So we have successfully established that this is a spanning set because we can express any arbitrary element as a linear combination of given three elements. Therefore, this is a set. B1 is a spanning set. So what is the dimension of V?
3.
4.
Yeah. We have a three element set. No, it's 3.
Yes.
So this claim is actually justified. Now, the other doubt that why don't we take elements like, I just write this inside a bracket as B1 prime. If I take, since I know that the 4 element set does span the whole space, so it should be able to span this too. Something like this if I take. The problem with this is the second element and the third element in this set do not belong to the vector space that you're considering. The vector space that you're considering is not all of M2 cross 2. Is this a symmetric matrix? Is this a symmetric matrix?
No.
The off-diagonal elements should be mirrored, right? Aij should be equal to Aji. In this case, A12 is not equal to A21. So these are not elements from your vector space itself. So if you want a basis of the given vector space, then you need to consider elements in the vector space. That is why we have this second element to be 0, 1, 1, 0. And since there is a condition which forces one of the four variables, four variables meaning, so M2 cross 2 has 4 entries. And then when I consider the subspace of symmetric matrices, one of those entries is dependent on one more entry. So there I lose one dimension. This is something very just philosophically I'm saying. The rigorous proof is this, that you actually explicitly construct a 3-element set. But if you want to understand it, or if you want to think about it intuitively, increasing the number of conditions decreases the dimension of your subspace that you consider. Here there is one condition which imposes a restriction on one of the elements. So from a 4-dimension set, you will lose 1 dimension to get this. I won't spend too much time on this, but symmetric matrices in n cross n R. So this is my V. Do you know what dimension of V is?
Is it n into n plus 1 by 2?
Yes, it is n into n plus 1 by 2, but how did you come up with that?
So I made it intuitively, like for each matrix we can, what we basically want is like a diagonal and the lower triangle. So in the first row it is 1 element, second row it will be 2 elements, something like that. So till last.
Yeah, that's correct. I'll just slightly expand on what he just said. If you don't understand this entirely, it's fine. So in a symmetric matrix, you have the diagonal elements. Let's call it A11, A22, ANN. But on either side of the diagonals, you have the same elements. For example, A21. This I can write it as A21 itself. So this is sort of dependent. So over here, you have one element, and if you take these 2 elements, in the next step you take 3 elements, and in the last step you take n elements, all of these are sort of independent variables, and the other elements depend on these. So if you count all of the matrices, you can explicitly write down a basis 2. That maybe I'll hint at what that will be. You will get 1 plus 2 plus 3 plus so on up to n. The sum of first n numbers is n into n plus 1 by 2. Specifically for 2, if you see, it is 2 into 2 plus 1 by 2, which is just 3. A basis for this would be of the form. So you'll have to take all of these things, 1, 0, 0, 0, 0, and then 0, 1, 0, 0, S star 0. All of these are there. There are n many of these, and then you'll have to take one element in each of the upper or lower diagonal. You take this as an exercise. If you don't get it, you can ask it in the next session. And it is not very important. If you're more mathematically inclined, you can try this out. Most of the time over here, we'll have explicit numbers. And just if you get too confused with general n, try it for 3 dimensions. What is the dimension of V3 supposed to be? V3 meaning 3 cross 3 symmetric matrices. According to this formula, it will be 3 into 3 plus 1 by 2, right? And what is that? It has to be 6. And a basis for such a thing would be 1, 0, 0, this, this. So these 3 elements are always going to be there, or these n elements in more generally. So I'll just write it in reverse just to. This is completely separately sort of messy thing. So if I look at the other elements, as soon as I determine this gets determined because you want a symmetric matrix. So I really have only 3 choices, this, and this. where I can put the ones. The rest get determined. And this. You can check that this is a basis. More generally, you will get one basis element for each diagonal entry, which there are 9 of. And then you'll get one basis element for each off diagonal entry, either in the upper side or in the lower side, because one of them determines the other. So that's symmetric matrices. And then let's take maybe 2 more. We'll quickly do this. Scalar matrices in, let's say, M3 cross 3. This is V. So what is dimension of V? First, just guesses. You don't need to be right. Just what do you think?
Is it 3?
3, sir.
So we have guesses 3. Any other guesses?
1.
There's 1. So this is a 9-dimensional vector space that we are considering the subspace of. So it's definitely less than 9. So that preliminary check is fine. Both the guesses are within that range. Now let us see what scalar matrices are. What are scalar matrices? What is a typical element of a scalar matrix look like?
Sir, A000 A0 0A0 008.
And A is free to be in real numbers. So as soon as you see this, how many free variables are there? How many degrees of freedom? There's really only one variable. But to see actually that is the case, can you give me a 1-element set which is a basis for this space?
Identity matrix of order 3.
Yeah. So if I take the identity matrix of order 3, any 1-element set, as long as it is non-zero, is linearly independent. Linear independence comes for free if it's just a 1-element set. If it is 2 elements, then you have to check if it's multiple of the other. If it is more than 2, then you have to set up this general equation and try to see what coefficients can give you a linear combination which equates to 0. But in this case, it's for free. The B is linearly independent is fine. Is it spanning?
Yes.
Yeah. So your typical element looks like A00, 0A0, 00A, which can, of course, be written as A times identity. I'll just write it as I3. A times identity. So, yeah, this is spanning. This is spanning. This is linearly independent. So this is a basis. So what is the dimension?
1, sir.
1, sir.
Now, scalar matrices were very specific kinds of matrices. I won't write all of this down. I'll just ask you verbally and you answer. What about diagonal matrices?
Sir, it will be 3.
Any other guesses?
It will be 3.
Okay. It will actually be 3. And the basis, a particular one basis for that would just be 1 in the 1-1 entry, 1 in the 2-2 entry, 1 in the 3-3 entry. So whatever we had called Eij earlier, it's just E11, E22, E33. All off diagonal entries are always 0 for diagonal matrices, and the diagonal entries are allowed to be different. And you can easily check that. Take any random diagonal matrix, and that can be written as a linear combination of these three matrices. So that's diagonal matrices. Now, the last sort of general example, which will probably okay. Before that, just general versions of these examples itself. Scalar matrices in n cross n. What will be the dimension?
1.
Any other guesses?
3.
Scalar matrix always the dimension is 1.
Scalar matrix is defined only for diagonal square matrix, no?
Yeah, take it n cross n. I'm saying it need not be 3. Just take any n cross n and just take scalar matrices in that. But that would still be spanned by solo identity element, right? All the diagonal entries are the same. So in any dimension, for any n, m cross n, the scalar matrices will have dimension 1. But what about diagonal matrices in n cross n r?
All the diagonal entries. How many diagonals are there?
Yeah, how many are there in n cross n?
M.
Yeah, whatever that n is, right? So if I have n cross n, this n number of diagonal elements will be there, and all of those are sort of free variables. So you can explicitly write down basis for all of these things. I will not write each of them. Let's take some.
Sir, how scalar matrices have a dimension n cross n, sir?
Scalar matrices will always have dimension 1. Diagonal matrices will have dimension n.
But it should be square now. Scalars are.
Just one moment. More generally, if V is the set of scalar matrices in n cross n r, then dimension of V is 1. Is this fine?
Yes.
Are you okay with this statement? Okay.
Yes, sir.
Now, if diagonal is replaced by scalar, over here it will be 3. Over here it will be n in general. That's what I was just saying. I'm not going to write it. But when you're studying vector spaces, you will have come across even more examples. You can try for your practice to see what the dimension is. And it's okay to guess something in the beginning and then train your intuition on your guess. Like if your guess went wrong, then see what about your initial intuition was going wrong, and then that is how you will understand it better. Now let's take XYZ R3. This is a subspace of R3 such that I'll just take something simple. What is the dimension of this? What is the guess?
2.
It's dimension
Anyone
1.
else?
Sir, 2.
Okay, there's 2 or 1. That is pretty much it, because you want it to be less than 3. It's not the entire space, so it should be less than that, and it can't be 0 because this is definitely a non-trivial set. So let's see. You can do the addition method that we had discussed in the last session, but here you observe that x plus y minus z is equal to 0. This has to be satisfied by all elements. So I can write z is equal to x plus y. Right? This has to be satisfied by every element in the set. So a typical element would look like x, y, x plus y. Is that okay?
Yes.
Yeah.
Now can I write this as some linear combination?
So
Can you
taking out the
decompose this?
The first
Which
vector can
sides
be
of
1, 0, 1, and the second vector can be 0, 1, 1, and x, y.
So I can do this. Right? So every element, what is this? Let us decode what we have done. What we have done is every element of V can be written as a linear combination of 0, 1, 1 and 1, 0, 1 and 0, 1, 1. So what does that actually mean?
these are the bases dimension.
This immediately does not say that this is the basis. There is one more check that needs to be done.
This
So
is
this just
spanning.
says that, yeah. So this spans V. If I can write every element as a linear combination of certain given elements, then I can say that that set spans my vector space. But in this case, you sort of get linear independence for free because it's a two-element set. So is this linearly independent or not?
Yes, sir.
Why is it linearly independent?
Because we cannot represent one vector as the other one, as a scalar multiple of the other.
Yeah, one is not a multiple of the other. This is a two-element set. So this is linearly independent. S is linearly independent, and hence, what is the word that I need to write?
Basis.
So this is the basis. Therefore, dimension of V
2.
Yeah, this is 2. Dimension of V is 2. And if you want to understand what actually dimension, you don't need to raise your hand. You can just speak up if you have a doubt.
So can you just explain one more time, sir, this last calculation?
Yeah, so I took a random element xyz in the vector space. My vector space is given by the condition that they are triples x, y, z such that x plus y minus z is equal to 0. I rearrange that, I get z is equal to x plus y. So any typical element would look like this, correct? X, y, x plus y, because z is equal to x plus y. That part is fine.
Yes, sir.
Then you decompose this x plus x, x, y, x plus y as x times 101 plus y times 011. You have these two things, right? X and y. You're just separating them out using just laws of vector addition. Because here we are in the usual vector space, usual meaning standard, plus and dot. So you're just you're just separating out the x and y. And what we discover is that this arbitrary element of the vector space that we chose or that we considered can be written as a linear combination of 101 and 011. So 101 and 011, they span V. Is this statement okay for you?
Sir, is spanning coming because of linear independence? Because they are linearly independent.
No, spanning and linearly independent are different things. Spanning means every element in the set can be written as a linear combination of vectors from the given set. Then we would say the given set spans V. So here we did express that every element of V can be written as a linear combination of this and this, which is the definition of spanning.
Okay.
Okay, if you are confused, maybe revisit the definition of span. Spanning means we take the given vectors and take all possible linear combinations. So the span of a set contains all possible linear combinations. Here we saw that any element does belong to the span. So the span of this does contain V, and it's also linearly independent, so it's a basis. There are two conditions, spanning and linear independence, that need to be satisfied for a set to be a basis. Here we have verified both conditions, and since the size of the basis is 2, we conclude that the dimension is 2.
Sir, here we have x plus y, then how it is linearly independent, sir?
X and Y are two different things, right? So here you have, when I'm talking about linear independence, I'm talking about this set. S is this two element set, which is 1, 0, 1 and 0, 1, 1. Is that not a linearly independent set?
Yeah.
Can you write any of the elements as a linear combination of any others? Which in this case just means, can you write one element as a multiple of the other?
No.
So this is a linearly independent set. This is also a spanning
Okay,
set, which means it's a
Got it,
basis,
sir.
which means the dimension
it.
is 2. All right. So this is about dimension. The size of a basis is the dimension, and how to verify whether something is a basis. How to construct a basis is something that we have discussed last time, where we had two methods, addition method and deletion method. You start out with an empty set, keep adding linearly independent vectors until you can span everything. That is the addition method. And the deletion method is, you start out with a spanning set, and then you keep deleting linearly dependent vectors until you obtain a linearly independent set. So there was a little bit of choice. Like you start off with a spanning set, and then you have to see which of the vectors depends on which of the other vectors. Things may not be very clear, correct? So let us take an example. I'll just do this thing here. In this case, you already know of a easier method to verify whether or not this is a basis. So how would you go about seeing whether or not this is a basis with whatever you know so far?
For checking linear independence, I will calculate determinant of these three vectors.
So these are elements in R3, right?
Yes.
Yeah. So what is the span of this set? What can be the span of this set? The span of this set is a subspace of R3. So it could be dimension 1, 2, or 3. So it will be dimension 1, 2, or so if it has to be dimension 3, then these three have to be linearly independent. Is that statement fine?
No, sir.
The statement is not clear, is it?
Sir, I'm saying that this is not linearly independent set because the V3 can be expressed as V1 plus V2.
V3 is not V1 plus V2.
No, sir. 2 times V2 plus minus V1.
2 times V2 minus V1 will work. Yes. So in general, how would you do it if it was not this obvious? It's 3 vectors in R3. N vectors in Rn is always easy.
So it is a determinant, we can find it.
Yeah, you can use determinant. You can, okay. So first thing we do is
we can use reduction method also.
So we can use Gaussian elimination, right?
Yeah, but we have not discussed that so far. Otherwise, you can take the determinant of this 1, 2, 3, 4, 5, 6, 7, 8, 9. You can check that this is 0, which means that this is linearly dependent. But now we'll discuss another method which will work for non-square matrices also, where such a thing may not be immediately obvious. You cannot see and just conclude that, okay, this can be written as, there'll of course be examples like that. So we'll have to be equipped to deal with that as well. So what we do is row reduction.
For determinant, we need to arrange in column wise or row wise, sir. So
in this case, both of them will work because determinant of the transpose and determinant of the matrix are the same, right? So if I put it as rows and I put it as columns, you'll just get transposes of each other. In the context of determinant, it's the same.
okay.
So if here I put rows, correct? So what if I put as columns? 1, 2, 3, 4, 5, 6, 7, 8, 9. This matrix is just the transpose of this matrix. Right? This is R, this is C. So let me call this MR is just MC transpose. And determinant does not change when you take the transpose.
Okay, so if it is not, sorry, if it is not equal to transpose means, then we need to arrange by column, right?
No, so if you're taking n vectors in Rn, if you arrange it in rows or arrange it in columns, you'll always get transposes of each other. So for the particular context of this problem, it does not matter.
Okay.
Okay, but there are, so next I will discuss row method and column method for the general case where you might not have square matrices. There the order matters. So the other thing that we can do is arrange this in such a way that the vectors are in the rows. And then do row reduction to get REF or RREF. So do you remember what REF and RREF is?
Yes, you reducing
reduction method, row echelon form.
So row application, sir.
So what is the first step that I will do to this matrix to get to go towards?
So make 0 to 4
Make
and 7.
leading entry
2 minus 4
make the
R1.
leading entry of rows is 1, sir.
So I'll do R2 minus 4R1 and R3 minus 7.
7 R1.
This I can start out with. This is a good starting point. So I do 1, 2, 3. I get a 0. This is why I did that. Minus 3 and minus 6. This would be 14. So minus 6 and 21, 9, 12. What next?
Divide the second
So
row by
we will divide minus 1 by 3.
Multiply by minus 1 by 3 or divide by minus 3. So either of them. Final step.
Minus plus 6 times of R.
So number of non-zero rows is equal to dimension of spans. So this is the general formula. So if you are given a set S with finitely many vectors, what you have to do is arrange them in rows in a matrix and then get it to the row echelon form. You can go and do the reduced row echelon form also, but that will not change anything because it will not change the number of non-zero rows. So this is in row echelon form, right? The final matrix. You have ones over here, and all the conditions are satisfied. The non-zero rows are below the zero rows are below the non-zero rows. Every leading entry is 1. All those conditions are satisfied. How many non-zero rows are there?
2, sir.
2.
2.
2 non-zero rows. So therefore, dimension of span is 2. Now dimension of span is 2 and I have 3 vectors, means that this is a linearly dependent set, right? If it was a linearly independent set, then this would be a basis and the dimension would be 3. That is not the case, which means that there is, so here we did observe that V3 can be written as a linear combination of V2 and V1. But this is the more general method where if you are given a finite number of vectors, then and you'll always be given a finite number of vectors, and you want to find the dimension of the span of the vectors. You don't know whether there are redundancies, you don't know whether there are linearly dependent vectors. So the deletion method does tell you that when you just check if some vector is a linear combination of the others and then remove it. But that is not an algorithm, right? That is not, there is no check that you can do. You have to pick each of them and try to express it as the linear combination of the others, which is not a very well-defined way. The more well-defined way again comes from row reduction method. And you take the vectors, place them as the rows of a matrix, row reduce that to get the REF, and then count the number of non-zero rows. This gives you the dimension of the span of the set that is given to you. Is that fine?
So the dimension of span of S is 2 right here.
In this case, it is 2, yes.
Okay. So when we consider as a matrix, so we have to write it as a 6 dimension previously in Indian. So could you please explain what is the difference? Like previously we have 2 into 3 matrix, that's a 6 dimension, and here it is dimensional span of S is 2.
This is dimension of span of S, right? There I had taken all possible matrices.
So that is for the matrix.
That is the space of all matrices. This is the space of 3-dimensional vectors, which are span of these vectors. Now I don't know if there is dependency or not a priori. So this is not a matrix space. This is a space of just vectors in R3. This is a subspace of R3, and I want to determine the dimension of that. And this method tells me that the dimension is 2. So just to see what's happening, let's take a sort of a trivial example. This is in R3. So this is a 2-element set in R3. What do you think the dimension of span S is? Just by looking at it.
1.
It's 1.
1, sir.
This is 1. Why is it? Because one of them is a multiple of the other. So, and if you just take linear combinations, you'll just get scalar multiples of 1, 1, 1. So any element in your vector space that is span S is just AAA. But
So
let's see what the...
In this case, then 3 cross 3, 9 dimensions 9. So all 9 vectors, right, are independent.
In which one? In this example?
There, dimension. So the same question what Ilango asked. So earlier the dimension of the matrix 3 cross 3, 9 we studied. You explained, right? So this comparing to the latest one. So here we can able to understand these 3 vectors are there. One is dependent. So then our dimension span is 2. So because 2 vectors.
See, earlier when I was talking about these matrix spaces, there we had considered the vector space of matrices. The vector space itself, the vectors itself were matrices. Over here, we have elements of R3. These are not matrices. I am arranging them in a matrix, which happens to be 3 cross 3 in this case. But a matrix does not have a dimension. It has an order. This is a 3 cross 3 matrix. but a matrix itself does not have something called dimension. A vector space has a dimension. Over here, I'm trying to determine the dimension of the vector space, which is given by span S. I'm given a finite set S, which will have a span, which will have a dimension. Now, since S is a subset of the vector space R3, the span of S is a vector subspace of R3. So it will have dimension 0, 1, 2, or 3. To determine what that number actually is, there are some ad hoc methods like see whether if one of them is a linear combination of the other. In some cases, you can use determinant to conclude whether they are dependent or not. But the algorithm that is going to work every time is arrange them as the rows of a matrix, perform row reduction, get it to the REF, and look at the number of non-zero rows. That happens to be the dimension of the span.
Dimension of the span means dimension of the spanning set, right?
No, so this S is a finite set. You have span of S. Span of S is set of all linear combinations, which is a vector subspace. So span of S is all possible linear combinations. You take summation AI Vi, where Vi is in S and AI is in R. So this is all possible linear combinations. This happens to be a vector subspace. And we are trying to look for the dimension of that.
Okay.
So in this case, that matrix 3 cross 3, it's an entire space, right? That is only you're telling. So then maybe we can consider every element is a one vector. Then we can tell if it is all independent, then the dimension is for entire space is 9, 3 cross 3, right?
We are not dealing with a 9-dimensional space in this example. We are dealing with a 3-dimensional space, which is R3. Even if all of these were linearly independent, then the dimension would have been 3, because you would get 3 non-zero rows over here.
This okay, sir. This okay, sir. Earlier you mentioned, right? It's a matrix 3 into 3 is a dimension 9. So that only just
that is an entirely different thing. There, a spanning set itself would be would have 9 elements. So over here you had 6 elements.
Yeah, that's what I'm telling. So which means 9 we can consider as a 9 independent vectors, like that we can tell. So for that,
if your space was M3 cross 3, then you can construct a 9-element set linearly independent, and that if it is also spanning, it will be a basis. Yeah, there you can construct a basis, but that is not related to this example, because here we are only dealing with subspaces of Rn. This method works for subspaces of Rn for which a spanning set is known.
Okay.
So let me write that. So let me complete this example. So what does my method say? If I want to determine this dimension of the span of S, we already observed that the dimension of the span of S is 1. So let's just go through the procedure. I'll write this as rows and do row reduction. So what is row reduction? Over here.
R2 change to
R2 minus 2 R1.
I get 1, 1, 1, 0, 0, 0. This is already in RREF. So what is the number of non-zero rows?
1.
1. So the dimension is 1. So we have formally verified it also. We, of course, as soon as we saw the set, we could deduce that the dimension is 1. But that will not always be the case. So you have to do this is the algorithm to find the dimension. This also happens to be a way to get a basis. That is what we'll see in the remainder of the lecture, this session. Now, yeah. To drive that point home, I need to take a specific example. I'll take easy examples first. Okay. I'll just put a remark. this method is used to find dimension of span S when S is a subspace of Rn, subset in this case. This is not for arbitrary vector spaces. There's a way to make it that way also, but yeah, for in the context of this course, just know that this is when you are given a spanning set of vectors in Rn, how do you get the dimension? Is this method clear?
Yes, sir.
Yes.
Okay. Now let's take this example. This will again be very simple. And let's say this is S. So just by looking at it, what do you think the dimension of the span is?
2.
So why is it 2? There are 3 vectors. It could be 3, but it is not. Why?
One is dependent.
Yeah. So the second vector is just a scalar multiple of the first vector. And the third vector is linearly independent. So if this was again, say something like -100, then the dimension would just be 1. So it's not just that there will be only one redundant vector. There could be many. But in this case, since V2 is just 2 times V1, that I can remove. Just by using the deletion method, I can just remove the thing and say that dimension is this. But let us. So, okay, what does dimension of span of S is equal to 2 mean? So what is dimension? Dimension is the cardinality or the number of elements in a basis, right? So can you give me a basis for this, for span of S?
We can just take S and remove either V1 or V2.
Basis for S. This works. Or we could have removed V2 also. That also works. But you cannot remove V3, right?
Yes.
If I remove V3, then I'll just get a one-dimensional space. I'm essentially removing the required thing. But once again, over here, whatever you're saying is specific to this example. You're looking at the example. In this case, it is very simple to see that which one is the one that has to be removed and so on. Now, if I give you more complicated examples, are you okay with the statement that it may not be easy to see which is the one that has to be removed? Can you see that in the general scenario, you will not have it so easy?
Just by looking, we can't tell that it's
Yeah,
basis
not
or
always. You can just look at it and say which one of them is the dependent one, which one of them is not. And doing trial and error is inefficient. So how to construct a basis? So how to get the dimension? We have already seen number of non-zero rows. Now let us see how to get a basis, an explicit basis. Just for completion, let me do the row reduction for this as well. The first step would be what?
R2 minus 2.
So that will give me this. And then what do I do?
shift the
Sir, interchanging R2 with R3, sir.
So this is my REF. So
Non-zero rows R2, sir.
So the dimension of V is 2 is fine. This was what we were expecting. This is what we are already know. V meaning span of S. Now, in order to construct a basis, all you need to do is just write down the non-zero columns. So dimension is given by number of non-zero rows and basis
Non-zero column.
is given by non-zero rows. So in this case, it is 1, 0, 0 and 0, 1, 0. That happens to be a basis very clearly. Over here also, we got it. We may not get the same thing. Just to show that, I'll take up another example. Let's take 1, 2, 3. Let's say 1, 1, 1. And then let me take, since we have been doing R3 stuff, let's do something else. Let's take 3 vectors in R4. Something like this. Is it obvious that this is linearly independent?
Yes, it is.
How so?
Because there is no linear combination of other two.
Yeah, how can you say that? You need some proof, right? You need to work that out. What about this? I mean, yeah.
So this is not linear independent
Yeah,
because
so
vector 1 is
there
the
I,
combination of vector 2 and 3.
yes, but how did you immediately say that there is no linear combination? Right, it's not obvious to, at least to me, as soon as I see it.
Sir, we have to go by basic principles that we take the linear combination of these three vectors and equate it to 0 and then
Yes,
solve
you
the
could do
equation.
that. Yeah, yes, you could do that. Or we can take up this Gaussian elimination or row reduction method. So if the dimension of the space that is spanned by this is 3, then these have to be linearly independent, right?
Yes.
So I'll just speed through this. Maybe you guys are faster, but yeah. 0 minus 1 minus 3 minus 3 0 0 1 3 plus. Well, I'll just do also minus 1 into this over here. Minus 1 into new R2. Skipping a few steps, but yeah, by now you should be comfortable with this. And this will just be 1 minus 1.
It will be 1 and 1, right?
Is it not minus 2 minus 2? Okay. Yeah. Minus 2, right. Yeah, it will be 1 1. Now, in this case, the dimension is 3. So what is a spanning set? the given set itself is actually a basis, but this is also a basis. If you go by the method, you will get this as the basis. It says that this is also a basis for S. Now, if I take that other example that I was briefly mentioning, like 1, 2, 3, 4, what was it? 1, 1, 1, 1, and 0, 1, 2, 3. So if suppose this is the thing, and I do the row reduction again, I will get a 0 row. As observed earlier, one of them, the third row is a linear combination of the first two. This would again just be 1, 2, 3 after enough changes.
Correct.
So this will be 1, 2, 3, 4, 0, 1, 2, 3. So dimension is 2, and a basis over here is 1, 2, 3, 4, 0, 1, 2, 3. So this gives you actually an algorithm to get basis. In this case, once again, you could say that it is very clear that this is a linear combination of the others, and then I can remove one element and get the basis. But let's say you have maybe 4 vectors in R5 and stuff like that. So there it is, when it is not clear which is the linear combination of which ones and which ones are redundant, which ones can be removed, which cannot be removed, this will always give you a short way to arrive at a basis, to get the dimension and arrive at a basis. Is that fine?
Yes.
Okay. So this is called the row method.
In case if we are rearranging the rows, there will be a change in the vector we choose for basis.
No, we will choose the non-zero rows itself. Over here, for example, we made a change in we interchanged rows 2 and 3. But the basis turned out to be row 1 and row 2 itself. It will be the non-zero rows itself. So here, note that we are not looking at this and going back to the vectors and choosing those vectors. So, okay, maybe this example will make it clear. The vectors that you get as the final things in your basis may not even be the vectors in the set that you start out with. Let's take this. 2, 1, 2, 3, 4, 6, and 1 minus 1, 1. So what's the dimension of this? Can you just say? I don't think you can. I don't even know. So let me do the proper method. So here what I'll do is this. I'm doing R1 minus R2 because I don't want to get this divided by 2. So what I'll do is I'll do R1 minus R2 and then take a negative sign. I'll just do minus of that to get a 1 in the first position. This is actually minus 1 into 2, but fine. Now I can do this R2 minus 3R1 and R3 minus R1 to get what? 1, 3, 4, 0 minus 5 minus 6, 0 minus 4 minus 5. It turns out it's a 3-dimensional thing.
Sir, I have one doubt in the row method.
Yeah. Yes.
Sir, if we arrange those vectors as columns, then after doing the whole REF steps, then won't it be easy to identify which rows are linearly independent or dependent?
Yes, the column method is something that I've not discussed yet.
Okay.
So when I talk about that, I'll
Okay.
talk about. There you can actually get the vectors from the base set itself. So yeah, here if you continue, let me just do that. I guess. No, this will be 1, and this will be 6 by 5. It's 4, 5, 0, 0, 4 times 24 by 5, something like this. I can multiply that by whatever, and I'll get 1. So I'll just leave it at this. You can see that REF will come down to this. So what does the method say? The method says that a basis is 1, 3, 4, 0, 1, 6 by 5, and 0, 0, 1. None of the vectors are from your original spanning vectors. But the span of S can have infinitely many bases. That is the first fact that we saw. So it doesn't really matter if you don't get the vectors from the set that you started out with. In this case, all of this seems unnecessary because you have a three-dimensional set in R3, so you can maybe get even say the standard basis is a basis. But there will be, I'm not able to come up with the perfect example. There might be one more iteration, but let's stop over here. This is just the algorithm to generate the basis. Let's stop over here for the row method. Now I'll discuss what is the column method. So yeah, the point that I wanted to say is that even if you interchange the rows, that doesn't have any effect, since the algorithm says that you just list the non-zero rows and that will be your basis. Is that okay?
Okay.
Yeah. Now the column method is over here. Why did we call this the row method? Is that we arranged, so we had a set S that we started out with. We took the vectors from the set and put them as the rows of a matrix. Here what we do is we put them as the columns of a matrix. Let's take some easy examples first. Let's say something like this. This is in R4. This is visibly linearly independent. So let's do something like this. Let's take something that is linearly dependent. This would still be K. Yeah, maybe just this. Clearly linearly dependent, and the dimension is 2 because the addition of V1 and V3 gives me V2. But let's work with this. Now, instead of putting the vectors as the rows of a matrix, we put them as the columns of a matrix. So you see that there are 3 identical columns, right? So it's just this, this, and this. Is this fine? This is the REF. R3 minus R1, R4 minus R1. So the dimension, once again, number of non-zero rows is the dimension. Dimension of span of S is 2. Now for the basis, in this case again, of course, we'll not take rows now because we have arranged the vectors as the columns. And even among the columns, we don't take the columns themselves. So what we do over here in the column method is look at the pivots. The pivots are in which columns?
First and second.
The first and second. So V1 and V2, we consider V1 and V2, and that will be a basis. So what is V1? My first vector was 1, 0, 1, 1. Second one was 1, 1, 1, 1. So the difference between the row method and the column method, apart from the fact that you arrange them as rows and columns, is that in the row method, you look at the non-zero rows, and that will be your basis. But in the column method, you look at the pivot elements and look at the vectors which correspond to the number of the column which contains the pivot elements. In this case, it is V1 and V2. In the another trivial case that we had done earlier, which one was that? Let's take this thing. 1, 0, 0, 2, 0, 0, and 0, 1, 0.
This also looks like a non-zero only, right?
The number of non-zero rows, yes, because see, corresponding to every pivot, you are picking an element. Yeah. Meaning the number of the elements in your basis will be number of pivot elements. And number of pivot elements is exactly the number of non-zero rows. Every non-zero row contains a pivot element, right?
Yeah.
So the dimension will be exactly number of non-zero rows, that is common. But the way you get the basis will be different.
Yeah, so that area directly same line we took as basis. Here we considering the set based on the number of pivot.
Yeah, we are looking at the column number which contains the pivots, and then looking at the corresponding vectors in the original set.
Okay.
Can we do that in the row method as well? Is it basis for the vector space then? In row method also, it is the same from the original vector we are taking it.
You can, okay. So here let's do that for this. Once again, trivial thing, trivial in the sense that as soon as you see it, you can get it. So in the row method, you'll start out with something like this. And in the second step, you'll get this, right? 0, 0, 0, 0, 3, 0. I'll make it 0, 1, 0. And then I'll interchange it and I'll get 1, 0, 0, 0, 1, 0, 0, 0, 0. Now, if I look at the pivots, this is the row method, remember. If I look at the pivots, they are in V1 and they're in column 1 and column 2, or row 1 and row 2, if you want to modify the method for row. But then if you pick the first vector and the second vector, that is not going to work. That is not going to be a basis. Right?
Yes. Yeah.
So row method will not always work in the same way that column method works. So here, but what does the row method says? It doesn't. It says don't look at the original set of vectors that you started out with. You just look at the final form. Just pick the non-zero rows from there. This is what it says.
So if question comes like we have to choose the basis from the original set, we have to approach with the column method, right?
Yes, but I cannot see the formulation of a question which forces you to use one of the methods. That could be, I don't know, because since this is all objective multiple choice type questions, right? So yeah, no, just know that this is the thing. The questions, yeah, if the questions ask that you have to choose the vectors from the given set, then yeah, you have to use the column method.
No, sometimes the options will be like that. The basis with row method, whatever we are getting, that will be there. Other than that, from the original set also, they would have given the options. So in that
Okay.
case, we have to choose two options, right?
Yeah. So column method, if the thing allows for if the question is worded in such a way that only the column method is applicable, then yeah, you have to use the column method.
Okay, thank you.
So in this case, what do I have to do? I just have to multiply the second row by 1 by 3, and I'll get this. Now what is 100, 200, 030? Yeah, the column thing was correct. Now when I look at the pivots, what columns are the pivots in?
1 and 3.
1 and 3.
So 1 and 3. So what are the vectors that I have to choose to get a basis?
V1 and
1
V3.
0 0.
V1 and V3.
V1 and V3, which are 100 and 030. So yeah, row method gets you a basis, but column methods gets you a
Sir,
basis
both
which
can be
is
basis. Both can be basis.
both are basis. Basis, there are infinitely many of them. That is what we were discussing in the beginning. Okay, so that's all about column method and row method. Yeah.
Sir, can you move the screen a little out?
This much
So
or
here,
further above?
no sir, here. Sir, here S is equals to 100 and 200 in that one. We have written basis is equals to 100 and 010, the one you have gotten after the row echelon form. You've not written the
Yes.
original one that was in that S.
Yes, that is sort of the point. Like the row method does not necessarily give you vectors from your original set. It gives you a basis which for the span of S. It gives you a basis for the span of S. It does not guarantee. So take for example, if this was not 100 and if this was a 700, you would have started with 700, made this 100, and then you would still get, by the row method, you would have got 100010, but the original vector is 7. Right. So there is no guarantee that even over here in the last example that I did, we started out with this set 2, 1, 2, 3, 4, 6, 1, minus 1, 1. But the basis that we got comprised entirely different vectors 1, 3, 4, 0, 1, 6, 5, 5, and 0, 0, 1. Right.
So, but there was again one place right there. S dash is equals to 100. In that one, you have written B equals to the original numbers.
Which
So here,
one? Where?
after the heading of no, go down a little down. There, the column method, and then you have written example S dash equals to. In that one, after you have
Oh, that's
solved
not S
it,
dash.
this is B equals to.
Yeah.
So
So
there
in the
is
column method, you will get vectors from the given set. In the row method, you need not. So here in the row method, you do not, but in the column method, you do.
okay. So it is a rule.
And by design, that's what happens. It's not a rule. Yeah, the rule dictates that this is what happens. So in the column method, what do? You look at the pivot entries, look at the column numbers of those, and choose the vectors from the original set which correspond to those numbers. But in the row method, you just do choose the non-zero rows. That's all.
In row method also, if we are not exchanging the rows, then we can take the corresponding.
Yes, no, that's a good point. But I don't want to confuse people with that.
Sir,
But your idea is correct.
So if you consider the basis in row and the column, we have the four vectors are there. So in this 100 is very common, and but another one is both different from the row and column. So
Okay, let me make a
maybe it will be
modification.
somewhat it is related. How, or it will be three vectors in basis. So how actually?
So here it's not at all related, right? 13401655001 is the basis that we got, but we started out with this set 2123461 minus 11.
Mm.
So it's not at all related. It is here it is related just by coincidence. Well, not entirely, because we chose a vector with 1 as the
No, no.
first entry.
My question at that I understood. My question is, see here the B here mentioning it's coming the combination of four related combinations are coming, right? So what I'm asking, maybe somewhat it is related, or we can tell because this is also so satisfying means this vector also we can tell basis means then we can consider we can tell three, right?
Three, what three?
Uh, Basis.
No, I'm not understanding your question.
So in row method we have two, and column method we have two. Okay, in this case one is same. Okay, another two is different, right?
What another two? So here, okay,
Zero
you're
one
saying that this is
zero
the same as
zero three.
this.
So yeah. So another vector is 010, and here column is 030. So means it's
Yes,
somewhat it is related. How we need to consider actually?
it is actually related, and you can actually write the relation because see what is happening to the vectors. You are doing row operations, and when you're doing row operations, you are actually just taking multiples of one vector, and in the row method at least, you are taking multiples of one vector and adding it or subtracting it from another vector. So if you keep track of all the changes that you're doing, you can actually find the relation between the basis that you get at the end and the basis that you started out with, or the elements that you started out with. This is probably also related to what she was saying, that if you don't
Yeah.
exchange the zero rows, then you can actually take just the row numbers and work with
Yeah.
that also.
Maybe it's somewhat related. So if you doing that
It is not
row,
somewhat
yeah.
related. It is precisely related in the way that you do the row operations,
Okay, okay, okay,
but it need not be the same elements as you start out with, is what I just stated earlier, and that still holds.
okay, okay.
I'm not going to go into more than that because it's somewhat unnecessary. Like, you don't need to keep track of the row operations and look at the corresponding changes to the vectors done. But what do you mean by row operations in the row method? You are just taking multiples of one vector and subtracting it or adding it to another, or scaling the vectors, or interchanging the vectors. So if you keep track of all of that, all of what is happening there, you will find the relationship between the vectors that you started out with and the vectors that you ended up with.
Got it, got it. Thank you.
Okay. So we are almost out of time. There is one important concept that needs to be covered. That is rank of a matrix. So this will be something that is relevant even much later on. And right now it might seem a little out of place, but it is still, it's a very important concept that keeps coming up later also. So don't forget about it, but at least keep aside all of these things that we are doing, arranging a vector, arranging a given set of vectors into a matrix and all that. Suppose you just have a matrix. Let me take a 2 cross 3 matrix. This is just an example, right? So if I look at the rows of this matrix, what are the rows? Sorry, the rows are, it's 2, 3, 1 and 0, 4. These are the rows. And what are the columns?
2
2,
0.
0
3, 4, 1,
8,
2.
and 1. Right now, these are vectors in their respective spaces. Like 2, 3, 1 and 0, 4, 2 are vectors in R3, and 2, 0, 3, 4 and 1, 2 are vectors in R2. So what is column space of A? This is span of
Columns of A.
columns. Oh, wow. Column. Okay. In this case, it is span of. I'll just write it as the row representation just because I want to write it in one line. And then you have something called row space of A, which is nothing but span of rows of A. Seems clear enough, right? In this case, it is span of 2, 3, 1 and 0, 4. Now to find the basis of this, you already know methods, row method, column method, whatever you want to do. You can go back to this thing, and if you arrange this as the rows of a matrix, what you get? You get this itself. And then you do your row operations and then get it into an REF form, determine what is its dimension, what is the basis. You can get all of that. But as sets, they are different. They sit in different spaces, right? If it's a square matrix that you're starting out with, your columns and rows will be in the same space. But in general, they need not be. In this case, you have one subspace of R2 and one subspace of R3. The important fact, which we will not prove, is dimension of column space of A is equal to dimension of row space.
Row space equals to rank.
It is very unclear just on first viewing that that should be the case. So this is some subspace of R3. It could be dimension 1 or 2 or 0. This is some subspace of R2, which could be 0, 1 or 2. It will not be 0. Neither of them will be 0. But it could be 1 or 2. But surprisingly, the dimension of both the spaces will be the same. It is not very difficult to see that because of the method that we have already discussed. If we use the row method on this, then it will be number of non-zero rows. Over here also it will be number of non-zero pivots, but I won't go into the proof. All you need to know is that these two things are equal, and the above quantity is called the rank of the matrix.
This should be equal to the rank of A.
This is the definition. Rank of the matrix denoted by rank. All right. So what is rank? Once again, it is the dimension of the subspace spanned by the columns of the matrix. It could be, you could take rows also. Because of this fact, it will be, both of them will be equal. And that is called the rank. Now, how to compute rank? It's the same as what you have already done before. Over here, you will not really have vectors that need to be arranged. You already have a matrix given to you. To compute rank, reduce the matrix to REF, number of this number of non-zero rows of REF is the rank. So this is a theme that will recur even more times, that you will have certain matrices, however you get them. In general, matrices, the dependence, linear dependence of rows and all that may not be obvious. The simplest version of a matrix is the REF. And just like in the case of system of equations, what did you do in the system of equations? You took your arbitrary coefficient matrix, brought it down to its REF, and REF is easy to solve. Similarly, to find the rank of a matrix just by looking at it may not be very easy. What do? You bring it down to REF. In REF, it is easy to calculate the rank. Rank is precisely equal to the number of non-zero rows. Correct? So even later on, you will see how row reduction will help us simplify general phenomena to more easily, like into forms which are easier to deal with. And this is one more instance of that. To calculate the rank, this is how you go about doing it. All right. So one quick statement which I would like you to think about and come up with an answer if possible is, if A is a M cross N matrix, if you already know this fact, then maybe don't answer. What is the maximum rank of maximum possible?
So minimum of M comma N.
Yeah, you seem to have known this beforehand, but okay, yeah. The answer is minimum of M comma N. Okay, can you say why it is minimum of M comma N? A quick
The number of
answer, quick reason. Yeah, go on.
it should be the number of elements in the column space of A, or the row space of A, which is equals to the dimension of the.
Yes, go ahead. That was not complete.
Yes, dimension of the means number of the elements in the basis, or the dimension, which is the same as the dimension.
So I'll just do a 2 cross 3 matrix. The 2 cross 3 matrix, an arbitrary 2 cross 3 matrix I'll take up. Let's just say it's A, B, C, D, E, F. Now, how can I compute rank? Is equal to number of non-zero rows?
Yes.
Not in the matrix, in its REF or RREF. Now, how many non-zero rows can be there?
2 maximum.
Maximum 2, sir.
2, right? Why? Because there are only 2 rows. So maximum rank is 2. But if you flip the thing around, 3 cross 2, and I have A, B, C, D, E, F. Once again, rank is the number of non-zero rows in the REF. But how many non-zero rows can be there?
2.
Three, sir, maybe. Can be
There
three.
are 3 rows. No, can there be 3 non-zero rows?
No.
So if I do the REF of this
More
after
than should be
whatever
there in the
number of
column.
steps, no, let's just do the REF of this. This will probably be 1,
Sir, it will
and
also have
this
2.
will be something. This should be 0. This should be 0. This is the best case scenario that we are working with, and this will be 1, and this has to be 0, right?
Right.
You cannot have more than this. You cannot have 3 non-zero rows. Every non-zero row should have a pivot, and you have only space for 2 pivots, because every pivot has to be strictly to the right of the previous pivot. Can you fit in 3 pivots in this?
No.
No, sir.
No, right? So once again, here you'll have max rank is 2, even though there are 3 rows. So now you think about this statement and try to come up with an argument for why it has to be minimum of m and n. I'll leave it at that, and if necessary, we can discuss it in the next session. So if you don't have doubts, feel free to leave. And if there are doubts, you can ask. First, let's take up doubts from the session, and then after that, we'll take up the GA doubts.
Can you just brief the difference between span and spanning set? I'm able to understand it, but sometimes it is get confused.
Okay, so span of a set. So if I have, this is done. So if I have any subset in a vector space V, I can talk about what is span of that set. Span of that set is the set of all possible linear combinations using vectors from that set itself. You can't choose any vectors. You have to choose a finite number of them. S itself could be infinite. You have to choose all possible finite linear combinations. Now, span S is a subset. This you can prove. Sorry, is a subspace. You have to verify that sum of 2 linear combinations is again a linear combination, and scalar multiples of linear combinations are linear combinations, both of which are not too difficult to prove. But for now, just take it that span of S is a subspace. So this is what is meant by span of a subset of a vector space. Now, a spanning set is now the other way. So what we have done is we started out with a subset, we got a subspace. What about the other way around? If I have a subspace, does it have a spanning set? Meaning, does there exist a set whose span is equal to this subspace? So that is a spanning set. So S is said to be a spanning set. Subspace meaning you can start out with any vector space. Subspace is again a vector space. Let me just call it W. All right. Spanning set for W if span of S is W. So first you start out with arbitrary vectors, like a subset of vectors, and in some way see what is the smallest subspace that contains that subset. That is called the span of that subset. Or you take all possible linear combinations and the set that you get happens to be a subspace, and it is called the span of S. But if you start out with any arbitrary vector space or a subspace of any vector space, does there exist a set for which the span of that set is equal to the vector space that you started out with? That is a question that we tried to answer in the last session also. So what we want is span of S is equal to W. But then we saw that there is an even more refined demand that we can do. We can also ask that the subset that we have be linearly independent. In that case, we will get even better properties for the set. So that happens to be a basis, a spanning set which is linearly independent. So given any vector space, I can find a finite set which is linearly independent and such that its linear combinations give me all vectors over here, all vectors in the vector space that I started with. So such a thing is called a basis. But if you just want to know what a spanning set is, it is a set such that its span is the given vector space.
So span is the subset of the vector space, and that vector subspace will be the spanning set. Is that what you?
No, you can start out with any subset. If you take all possible linear combinations. So okay, let's take maybe examples.
Yeah.
If I take just a single element set 0, 1, or maybe let's not take it so trivial, 2, 3. Now, if I take span of this, take span of S, what do I have to do by definition? Take all possible linear combinations using vectors from the set. But there's only one vector in the set. So linear combinations just means multiples. It becomes things of the form 2C, 3C, where C is in R. Is this fine?
Yes.
And what is that geometrically? It is some 2y is equal to 3x line.
Yes, it will be a line.
Right? X equal to 2, so this will be it'll be something like this. It'll be a line through the origin.
Yeah.
It will not be any line.
Yeah.
So similarly, if you have two elements in, let's say, R3, if you take all possible linear combinations, you'll get a plane and so on. So you can start out with finitely many elements, take all possible linear combinations. So to see that, let's take S prime is 1, 0, 0. I'll take trivial examples over here just to show you what's happening. So what are all possible linear combinations using vectors from this? It is A times the first vector plus B times the second vector. Now A, B could be 0, could be non-zero, whatever. But what will this give me? This will give me a point of the form A, B, 0.
Yes.
And A, B are free to take values in R. It's all possible linear combinations. So when I vary all possible A and B, what will I get in this case? Can you geometrically describe what is the set that I obtain?
R2, right?
This is in R3.
R3, but the space will be of two variables, right? A, B only.
It's of two variables. It does not have a Z coordinate. It's called a particular thing. Can you give me what I'm looking for?
So it's a plane.
It's a plane.
It is a plane. It's called a particular, it has a name. So what are the variables that are free to roam? It's called the XY plane.
Yeah, XY.
Right. So it's a bit messy over here, but so if this is X, Y, Z, it is just this plane. So there's no height. And that is a subspace. A single element set cannot be a subspace. Vector space has to be either trivial or it has to be infinite. It has to have infinite elements. So the set that you start out with may not be a subspace, but the span of it will always be a subspace. And now if you take the subspace which is the XY plane and ask what is a spanning set for the XY plane, 1, 0, 0, 0, 1, 0 is a spanning set. But there are more spanning sets also. You can take 1 0 0 0 1 0 1 1 0. That 1 1 0 is a redundant element, but still it's a spanning set. So and if you want a basis, then you will have to have linearly independent elements which span the given set.
Okay. Thank you.
Yeah.
Excuse me, sir.
Yeah.
Sir, the dimension of a vector space is basically its number of bases, right?
Number of elements in the basis.